Welcome to this very short video on probability spaces. This is just to give you a little bit of a background on abstract probability theory. You'll notice that in this handout that we're working on, which you can obtain at tutorweb.net, there is precious little on this topic. We could easily expand this into a full semester on probability theory, but we won't. We have basically a fundamental definition, which is what we mean mathematically by a probability space. So it's we start with a set, and we think of this as the set of possible outcomes. Call it a sample space. So if you're tossing a coin, for example, once, you can get either heads or tails, and this would be your sample space. If you toss a coin twice, the sample space would be the set of all possible combinations: heads, 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 tails, tails, heads, or tails, tails. So that's a sample space. Now, a different case is when the sample space is infinite. For example, any real number might be a possible outcome. And then the sample space is not only infinite, it's also uncountable. And then we need to resort to take some more care in our definitions. An event is simply a set, a potential outcome. So here we might consider the outcome of getting exactly one head, and that's actually these two possibilities. So that's an outcome. That's an event. The event of getting exactly one head or exactly one tail. We might consider the event of getting no heads. So that would be this one. And so it's an event with only one element, if you like. Or the event of getting at least one head, which would be the event with these three elements here. So events are just subsets of the sample space. Now, an event is a subset like this. Now, if we think about the collection of all possible subsets, then those are typically denoted by the power set of omega. So this is the set of all subsets. Now, the events which we're talking about are always a collection of sets. So they are naturally a subset of this full collection of all subsets. So in other words, the collection of sets we're looking at is a subset of the collection of all subsets. Now, it needs to satisfy certain criteria. So because we want to talk about the probability of something, the probability should be something between 0 and 1. And we're not just interested in the probabilities of individual outcomes. So it's not enough for us to talk about the probability of getting each of these. We also want to talk about the probability of getting certain events, so collections of outcomes. And of course, the probability needs to be between 0 and 1. The probability of an event, of an outcome of getting something, which is the probability of the whole space, needs to be 1. And the probability should always be positive. So these are the criteria that we have. The probability of any event is between 0 and 1. The probability of the entire sample space is equal to 1. And then we want to be able to add the probabilities of disjoint events. So in other words, the probability of getting this outcome or this outcome should be the sum of the two. So the probability of this event as a whole should be the sum of the probabilities of the subsets. Now, it's not enough, as it turns out, to do this only for finite subsets. So in the case of infinite sample spaces, we need the probability of a union of disjoint sets to be the sum of the probabilities of the individual sets. Now, this may not seem obvious initially why we need this, but a simple example will be enough. Suppose you have a distribution of probabilities on the integers 0, 1, 2, 3, and so forth. Then we need the probability of the entire, of getting something, of the entire collection to be 1, and that is by nature an infinite sum. So we do need this. We do need to be able to talk about infinite sums here. And of course, the entire sample space, which is the natural numbers and 0, is the union of the individual integers from 0 to infinity. So we need this countability thing. Now, what that's going to do is it's going to make us need to think a little bit about what sort of collections of sets we need. And in the case of the real line, it turns out you cannot just have the entire collection of all subsets. So what we want is we want subsets which are such that countable unions are also an element of the collection. So in other words, if all of the individual A's are in the collection of sets we're looking at, then the countable union also needs to be an element of the set. So that's simply a restriction on the collection. And such collections are called algebras. In other words, the entire sample space has to be an element of it. Countable unions of disjoint sets have to be parts of it, and complements also have to be a part of the sets. And a particularly useful such collection, such an algebra, is the Borel algebra of real numbers. And it's a collection of sets which satisfy these properties of countable unions being also contained in the algebra. But the algebra also contains all the half-closed intervals. Now it will follow then that it also contains unions of intervals. It will contain the R as a whole, because it needs to contain complements. And it will also, by using countable unions, contain open intervals, intervals that are half-closed, half-open to the left, and so forth. So it will contain all intervals, and it will be enough for all of the probabilities we look at to just use the Borel algebra. And a Borel algebra exists for the real line like this. It also exists for the interval from 0 to 1, for example, or any interval. We can talk about the Borel algebra simply being the smallest collection of sets which satisfy this criterion. It contains all of these, and it is an algebra. So it exists because the intersection of any two algebras is also an algebra, sigma algebra rather. The intersection of any two sigma algebras is also an algebra, and one of them exists. The collection of all subsets is a sigma algebra. So we have the property that a smallest collection must also exist. It's just the intersection of all of the sigma algebras which satisfy this criterion. And if I didn't say this originally, there's a distinction between an algebra and a sigma algebra. A sigma algebra has to contain the countable unions like we have here, but an algebra only has to contain finite unions. We require countable unions, so we're always talking about sigma algebras. So it's denoted sigma algebra. And that's enough on the abstract version. We then should, in our next little video, talk about conditional probabilities and such. But this is, as I mentioned in the overall introduction, this starts as a collection of short videos designed for the University of Iceland. If my students require videos on certain topics, then I will simply add them. So that it's possible to get to order your own if you like, if you're a member of the course. But I will be adding a certain minimal collection regardless whether any requests for them or not. So that's all for today. See you in the next video.